What if everything we thought we knew about the birth of the universe was flipped upside down? Picture this, a time so ancient that light itself had barely begun its journey across the cosmos. No glittering galaxies, no swirling nebulae, just an endless, shadowy ocean of gas and dust simmering with the raw ingredients of creation. In this primordial darkness, a cosmic mystery hides. Did planets form before galaxies? It sounds impossible, doesn't it? We've always assumed galaxies came first, those colossal cities of stars where planets eventually took shape. But what if the universe had other plans? Scientists are now uncovering clues that challenge this very foundation of astronomy. Tiny, ancient grains of dust, whispers of radiation from the edge of time, and the faint echoes of the first structures to emerge after the Big Bang, all hint at a story far stranger than we ever imagined. Could rogue planets, untethered from stars, have drifted through the darkness long before galaxies assembled? The idea reshapes not just our timeline of the cosmos, but our place within it. If planets came first, what does that mean for the origins of life itself? This is where the journey begins. We're about to travel back further than ever before, to an era when the universe was a blank canvas, and the rules we take for granted hadn't yet been written. Along the way, we'll meet the daring astronomers piecing together this puzzle, explore the mind-bending tools they use to peer into the past, and confront the astonishing possibility that the first worlds might have been born in total isolation. By the time we're done, you'll see the night sky and our cosmic history in a whole new light. So let's dive into the darkness together and uncover the secrets waiting at the dawn of time. The universe began not with a whisper, but with a roar, a searing burst of energy that set space and time into motion. In those first fleeting instants after the Big Bang, everything we know was compressed into a single point hotter than the core of any star today. There were no planets, no galaxies, not even atoms, just a swirling chaos of fundamental particles dancing at temperatures beyond comprehension. But as the cosmos expanded, it cooled, and like steam condensing into droplets, the first building blocks of matter began to take shape. Within minutes, protons and neutrons fused to form the simplest atomic nuclei, hydrogen and helium, the raw materials of all future cosmic structures. Yet for hundreds of millions of years, the universe remained a featureless void, illuminated only by a faint, uniform glow. Then, something extraordinary happened. Tiny ripples in the fabric of space, imprinted during the Big Bang itself, began to amplify. These ripples' slight variations in density acted like cosmic breadcrumbs, gathering matter through the relentless pull of gravity. Dark matter, that mysterious invisible scaffold of the universe, played a crucial role too, weaving an unseen web that guided ordinary matter into place. The first stars, known as Population 3 stars, flickered to life in this shadowy expanse. Unlike stars today, they were massive, short-lived behemoths, burning fiercely before exploding in spectacular supernovae. These violent deaths scattered heavier elements like carbon and oxygen across the cosmos, enriching the gas clouds that would birth future generations of stars. But here's where the plot thickens. Could some of that debris, those fragments of stardust, have clumped together fast enough to form planets even before galaxies took shape? The idea seems radical, but the universe in its youth was a place of incredible speed and chaos, where the rules we know today were still being written. To unravel this mystery, astronomers turned to the faint whispers of light from the universe's infancy, cosmic microwave background radiation, ancient quasars, and the chemical fingerprints of the first stars. Each clue paints a picture of a time when gravity was the artist, sculpting the cosmos one delicate structure at a time. Whether planets or galaxies came first isn't just a question of chronology. It's a window into how complexity emerges from simplicity and how the universe learned to build itself from the ground up. Dark matter is the universe's invisible architect, a ghostly presence that shaped everything without ever revealing itself. Think of it as the scaffolding for a skyscraper, holding the structure together long before the glass and steel are added. In the early cosmos, while ordinary matter was still a diffuse haze, dark matter had already begun to clump under its own gravity, weaving a hidden web across the void. These dense knots, called dark matter halos, became the gravitational anchors for everything that followed. Without them, galaxies might never have formed at all. But here's where the story takes a fascinating twist. Inside these halos, pockets of ordinary gas, hydrogen and helium began to pool, drawn in by the irresistible tug of dark matter's gravity. In the densest regions, temperatures soared and pressure mounted until nuclear fusion ignited, sparking the first stars. Yet some simulations suggest that not all of this gas became starlight. Tiny, isolated clumps might have collapsed into something far stranger, rogue planets, adrift in the darkness like cosmic orphans. Picture a world without a sun, born in the cold embrace of a dark matter halo, orbiting nothing but the halo's invisible core. It's a haunting idea, one that challenges our understanding of how planets form. Support for this theory comes from the way dark matter behaves. Unlike ordinary matter, it doesn't collide or radiate energy. It simply passes through itself, piling up in dense, smooth concentrations. This means dark matter halos could have nurtured pockets of gas stable enough to form planets, even before the turbulent birth of galaxies scattered them apart. Some astronomers speculate that these early rogue worlds might still exist today, lurking in the spaces between galaxies, relics of a time before the cosmic order we know took hold. The implications are staggering. If planets did form in these primordial halos, they could have provided the first solid surfaces in the universe, cold, dark, but perhaps not entirely lifeless. Without the deadly radiation of young stars, these worlds might have had underground oceans kept liquid by geothermal heat or dark matter annihilation. It's a long shot, but not impossible. After all, the early universe was a place of wild experimentation, where the rules were still being written. Every discovery peels back another layer, revealing just how little we truly know about the cosmos's first chapters. Those first stars were cosmic alchemist titans that transformed the simple elements of the early universe into something far more complex. Population 3 stars, as they're called, burned at temperatures and intensities we can barely fathom, their cores acting as celestial furnaces where hydrogen and helium fused into heavier elements like carbon, oxygen, and even iron. These weren't the stable, long-lived stars we see today. They were volatile giants, some hundreds of times more massive than our Sun, living fast and dying young in cataclysmic explosions. When these stars reached the end of their brief lives, they didn't fade quietly. Their deaths were spectacular supernovae, blasting newly forged elements across the cosmos in expanding shockwaves. This stardust, the ashes of those first stars, became the raw material for everything that followed: rocky planets, icy moons, and eventually, the chemistry of life itself. But here's the tantalizing question: could some of that debris have clumped together into planets while the universe was still in its infancy, before galaxies had fully taken shape? The challenge lies in the timeline. After the Big Bang, the universe was expanding rapidly and matter was spread thin. For planets to form, dust grains needed to collide, stick together, and grow into larger bodies, a process that typically takes millions of years. Yet in the dense environments around those first supernovae, conditions might have been just right for rapid planet formation. Simulations suggest that in the turbulent wake of a dying population, 3-star, swirling disks of gas and dust could have given birth to planets in mere thousands of years, a blink of an eye on cosmic scales. Some of these early worlds might have been flung into the void by gravitational interactions, becoming rogue planets drifting through the darkness. Others could have been captured later by emerging galaxies, becoming some of the oldest relics in the cosmos. The key to solving this mystery lies in the faint chemical signatures left behind. By studying the composition of ancient stars and distant gas clouds, astronomers are piecing together a timeline of when heavy elements first began clustering into solid bodies. If planets did form this early, it reshapes our understanding of how quickly complexity arose in the universe. We often think of cosmic history as a slow, gradual process, but what if the universe was building planets almost as soon as it had the ingredients to do so? It's a humbling reminder that the cosmos has always been full of surprises, defying our expectations at every turn. Imagine a cosmic construction site, where the wreckage of the first supernova isn't just debris, it's the raw material for something astonishing. In the chaotic aftermath of these stellar explosions, shockwaves rippled through the early universe, compressing clouds of gas and dust into swirling, disc-shaped nurseries. These weren't just any disks, they were the seeds of the very first planets forming in isolation, untethered from stars. Picture a world born in darkness, orbiting nothing but the memory of the explosion that created it. These protoplanetary disks would have been violent, chaotic places. Without the steadying influence of a star's gravity, clumps of dust collided and stuck together, growing into rocky bodies or icy worlds. Some might have been flung into the void by gravitational kicks, becoming rogue planets drifting through the cosmos. Others could have lingered near the remnants of their parent stars, frozen in the cold embrace of space. But here's the twist: even without sunlight, these worlds might not have been entirely lifeless. Deep beneath their icy surfaces, geothermal heat from radioactive decay, or even the faint warmth of dark matter annihilation could have maintained liquid water. On Earth, we've found microbes thriving in similarly extreme environments, like hydrothermal vents at the bottom of the ocean or buried deep in glaciers. If life can persist in those harsh conditions, why not on an ancient rogue planet? The chemistry would have been different, slower, but the building blocks were there. Water, organic molecules, and energy sources we're only beginning to understand. The real challenge is proving these worlds existed. Unlike stars, rogue planets emit almost no light, making them nearly invisible across cosmic distances. But astronomers have tricks up their sleeves. Gravitational microlensing, where a planet's gravity bends the light of a background star, could reveal their presence. Or we might spot them by their faint heat signatures, the last whispers of warmth from their formation billions of years ago. Every discovery pushes the boundaries of what we thought possible, forcing us to rethink not just where life could exist, but when it might have begun. If these primordial planets did form, they'd be the ultimate cosmic time capsules, frozen relics of a time before galaxies, before stars as we know them, even before light had fully escaped the universe's shadowy dawn. Their existence would rewrite the story of how quickly complexity emerged from chaos and how resilient life might truly be in the grand tapestry of the cosmos. The debate over what came first, planets or galaxies, has split astronomers into two camps, each armed with compelling arguments. On one side, traditional models paint a familiar picture. Galaxies formed first, acting as cosmic cradles where stars and planets could gradually take shape. These vast structures provided the stability needed for gas and dust to cool, collapse, and eventually coalesce into planetary systems like our own. It's a tidy narrative, one that fits neatly with our observations of mature galaxies brimming with planets today. But the early universe was anything but tidy. New simulations suggest a far more chaotic scene, where rogue planets might have formed in the turbulent aftermath of the first supernova, long before galaxies settled into their familiar shapes. A critical factor is speed, how quickly tiny dust grains could stick together in those primordial conditions. Under the right circumstances, gravity could have worked in overdrive, compressing debris into planet-sized clumps almost instantly. Picture a cosmic assembly line running at breakneck pace, churning out worlds faster than galaxies could even begin to organize. The evidence for this radical idea lies in the physics of dust itself. In dense, high-pressure environments like those surrounding early supernova, dust grains don't just drift lazily. They collide violently, shattering and reforming in a frenzied dance. Some studies show that under these extreme conditions, microscopic particles could have aggregated into kilometer-sized objects within just a few thousand years. That's fast enough to outpace the slow gravitational tug of war that builds galaxies. Yet skeptics argue that without the shelter of a galactic structure, these early planets would have been vulnerable, swept away by stellar winds or torn apart by gravitational forces. It's a bit like trying to build a sandcastle during a hurricane, but supporters counter that the universe's infancy was a place of strange possibilities, where rules we take for granted didn't always apply. Dark matter halos, for instance, might have provided hidden pockets of calm, shielding fledgling planets long enough for them to survive. The answer could lie in the oldest stars we can observe. By analyzing their chemical makeup, astronomers hunt for traces of planetary material that predates galactic formation. Finding such a fingerprint would be like discovering a fossil buried in the foundation of a city, proof that something ancient existed before the skyline took shape. Until then, the question remains open, a tantalizing reminder that the universe's earliest moments might still hold surprises we've yet to imagine. If the first planets still linger in the cosmos, they'd be the ultimate cosmic fossils, silent witnesses to an era before galaxies dominated the sky. But finding them is like searching for a single grain of sand in an endless desert. Some may have been devoured long ago, pulled into the swirling cores of young galaxies as they grew. Others could still wander the void between galaxies, frozen and dark, untouched by the light of any star. These lonely worlds would carry the chemical fingerprints of the universe's infancy, their very existence rewriting the story of how cosmic structures emerged. The hunt for these ancient relics hinges on a phenomenon called gravitational microlensing. When a rogue planet drifts in front of a distant star, its gravity acts like a lens, bending and magnifying the star's light for a fleeting moment. It's a cosmic wink, a subtle signal that betrays the presence of an otherwise invisible world. But catching these events is like trying to photograph a lightning bolt in a thunderstorm. They're rare, unpredictable, and vanish almost as quickly as they appear. Telescopes like the upcoming Nancy Grace Roman Space Telescope are designed to scan vast stretches of the sky, watching for these telltale flickers that could reveal planets adrift in the darkness. Even more tantalizing are the clues hidden in the oldest stars we've found. Some of these ancient giants contain unusual concentrations of heavy elements, as if they ingested planetary material long before their galactic homes took shape. It's like finding dinosaur bones in the foundation of a modern city, evidence that something much older lies buried beneath. If planets existed before galaxies, their remnants might still be scattered across the cosmos, waiting to be pieced together like fragments of a forgotten language. The challenge isn't just technical, it's philosophical. If we confirm that planets predate galaxies, it forces us to rethink how quickly complexity arose in the universe. Were planets the universe's first experiments in building order from chaos? And if so, could life have gotten an earlier start than we ever imagined? Every flicker of light, every odd chemical signature brings us closer to answers and to uncovering the lost chapters of our cosmic origins. Supermassive black holes aren't just cosmic vacuum cleaners. They're the universe's ultimate sculptors, shaping galaxies with gravity so powerful it bends space itself. At the heart of nearly every galaxy, including our own Milky Way, one of these monsters lurks, millions to billions of times heavier than the Sun. But here's the twist: some of them might have existed before galaxies even formed. Imagine a black hole so ancient it predates the city of stars it now calls home. If that's true, its gravity could have been the invisible hand guiding the first planets into existence, or tearing them apart before they had a chance to grow. The idea hinges on timing. Observations of distant quasars' bright beacons powered by supermassive black holes reveal they were already fully formed when the universe was less than 1 billion years old. That's shockingly fast, leaving astronomers scrambling to explain how such colossal objects could emerge so quickly. One possibility: they grew from the collapse of primordial gas clouds, or even from the remnants of those first massive population 3 stars. Once born, their gravity would have acted like a cosmic magnet, pulling in nearby gas and dust at a furious pace. In this chaotic environment, swirling disks of material around these black holes might have become accidental planet factories, compressing debris into solid worlds before the surrounding galaxy could take shape. But there's a darker side to this story. A supermassive black hole's appetite is legendary. Its tidal forces can stretch and shred anything that ventures too close, turning potential planets into scattered dust. Some theories suggest these black holes may have sterilized entire regions of the early universe, preventing planets from forming until the chaos subsided. Yet others argue their influence was more subtle, like a gardener pruning a tree. Their outbursts of energy might have cleared space for later, more stable planetary systems to emerge. The key to solving this riddle lies in the relationship between black holes and their galaxies. Today, we see a curious link: the bigger the galaxy, the bigger its central black hole. This suggests they grew together, each shaping the other's destiny. But if black holes came first, their gravity could have laid the groundwork for everything else, carving out pockets of stability where planets might have formed in isolation. Future telescopes, like the James Webb Space Telescope, are peering deeper into the past than ever before, searching for clues in the faint glow of the universe's dawn. Every new observation brings us closer to understanding whether these cosmic titans were destroyers, creators, or something far more unexpected. One thing's certain: the early universe was a battleground of forces we're only beginning to comprehend, where the rules of physics played out on a scale beyond imagination. Primordial planets sound like something straight out of science fiction worlds, born from the raw chaos of the early universe, untouched by the light of stars. But according to cutting-edge theoretical models, these exotic objects might not just be fantasy. Picture a time when the cosmos was a swirling sea of hydrogen and helium, still reeling from the violence of the Big Bang. In that primordial soup, tiny ripples in density imprinted during the universe's first moments could have created pockets where gravity worked in overdrive. These weren't the vast, majestic disks we associate with planet formation today. Instead, they were miniature whirlpools of gas collapsing directly into dense, planet-sized clumps without ever needing a star at their center. These hypothetical worlds would have been utterly alien compared to anything in our solar system. Imagine a planet made almost entirely of hydrogen and helium, with no rocky core or molten mantle, just a frigid, uniform ball of primordial gas. Some might have been as small as Pluto, while others could have rivaled Jupiter in size. Without a star to warm them, they'd have drifted through the darkness, their surfaces colder than the void of space itself. Yet even in that icy isolation, they might have held secrets. Deep beneath their gaseous exteriors, pressures could have been high enough to squeeze hydrogen into exotic states, like metallic hydrogen, a form that conducts electricity and might have generated weak magnetic fields. The real puzzle is how such delicate structures could have survived the turbulence of the early universe. After all, this was an era of extreme radiation, violent shocks from supernova, and the relentless pull of growing dark matter halos. One theory suggests that some of these primordial planets formed in the quiet outskirts of the first proto-galaxies, where densities were just right for collapse but shielded from the worst chaos. Others might have been born in the debris of early supernova, where heavy elements were still rare, leaving hydrogen and helium as the dominant building blocks. If these worlds did exist, their legacy might still be detectable. Astronomers speculate that some could have been captured later by forming galaxies, ending up as rogue planets in the halos of galaxies like our own. Others might have spiraled into the first stars, altering their chemical makeup in ways we could uncover by studying the oldest stars in the Milky Way. The James Webb Space Telescope is already hunting for clues, analyzing the atmospheres of distant gas giants for traces of primordial composition, an echo of a time when the universe was learning how to build planets in the dark. This isn't just about rewriting cosmic history, it's about redefining what a planet can be. We're so used to thinking of planets as companions to stars, but the early universe might have crafted them in solitude, as dark and silent as the void itself. Their existence would prove that planet formation isn't just a footnote in galactic evolution, it could be one of the universe's first acts of creation. Peering back to the dawn of time isn't just a technical challenge, it's like trying to read a book that's been left out in the rain, its pages faded and blurred by billions of years of cosmic expansion. The light from the universe's first structures has been stretched so far by the relentless growth of space that it's shifted entirely out of the visible spectrum, slipping into the infrared like a whisper lost in the wind. This isn't just a minor inconvenience, it means the very signals we're hunting, the faint glow of the first planets or proto-galaxies, are buried in a sea of noise, drowned out by the brilliance of younger, closer objects. Enter the James Webb Space Telescope, our most powerful time machine yet. With its gold-coated mirrors and suite of infrared instruments, it's designed to catch these elusive whispers from the cosmic dark ages. But even Webb faces a needle in a haystack problem. If early planets existed, they'd be cold, dark, and tiny, barely visible against the backdrop of the universe's glow. Their signatures might not be direct images but subtle fingerprints, a slight warping in the cosmic microwave background, the afterglow of the Big Bang, or unexpected shadows in the light of distant quasars as their light passes through primordial gas clouds. The real breakthrough could come from something called gravitational lensing, when a massive object like one of those hypothetical early planets passes in front of a more distant light source. Its gravity bends the light like a magnifying glass, creating a temporary brightening. Spotting these microlensing events in the early universe would be like finding footprints in ancient mud, proof that something solid once passed through the cosmic void. But the timing is fiendishly difficult. These events last hours to days, and with the vast distances involved, we're essentially trying to photograph a firefly's blink from halfway across the planet. Another clue might lie in the chemistry of the universe's oldest stars. Stars like He 1523-0901, born just a few 100 million years after the Big Bang, are cosmic archaeologists preserving elements from their birth environments in their atmospheres. If planets formed before galaxies, they'd have left behind traces of heavy elements carbon, silicon, iron, scattered in the gas clouds that birthed these stars. Finding stars with unusual metal patterns could hint at planetary debris predating their galactic homes, like discovering arrowheads in a layer of rock older than the city above it. The challenge isn't just technological, it's philosophical. Every observation we make is a snapshot of a universe that no longer exists, a puzzle where half the pieces are missing. If we do find evidence of planets before galaxies, it won't just rewrite textbooks, it'll force us to rethink how quickly complexity can emerge from chaos. The universe might have been building planets in the dark, long before the first stars lit up the sky, and we're only now beginning to glimpse that hidden chapter of cosmic history. Galaxies didn't emerge fully formed from the cosmic darkness. They were built piece by piece over eons, like a sprawling city slowly rising from the ruins of countless smaller towns. In the early universe, gravity acted as the ultimate architect, pulling together wispy clouds of gas and dark matter into fragile proto-galaxies. These infant structures were nothing like the majestic spirals or glowing ellipticals we see today. They were chaotic, unstable, and constantly colliding, merging and reshaping in a slow-motion ballet that spanned billions of years. This drawn-out timeline opens a tantalizing possibility. If galaxies took so long to assemble, what was happening in the quiet gaps between their formation? The first planets might have had a cosmic window of opportunity, forming in the sparse outskirts of these proto-galaxies or even in the vast, empty spaces between them. Without the crowded stellar neighborhoods of mature galaxies, these early worlds would have existed in near-total isolation, no nearby stars to warm them, no planetary siblings to disturb their orbits. Just cold, dark solitude, but here's the catch: the chemistry of these planets would have been unrecognizable compared to Earth. In those early epochs, the universe was still a pristine laboratory, dominated by hydrogen and helium. Heavier elements, carbon, oxygen, silicon, the very building blocks of rocky planets like ours, hadn't yet been forged in the hearts of stars and scattered by supernovae. Any planets forming then would likely have been gas giants, vast and diffuse, with no solid core or surface to stand on. Picture a Jupiter-like world, but colder and darker, drifting through the void like a ghost. Yet even these exotic worlds might have held surprises. Some theories suggest that without the intense radiation of nearby stars, their atmospheres could have cooled enough for exotic ices, like frozen nitrogen or methane, to form thick global crusts. Others propose that tidal forces from passing dark matter clumps or the faint warmth of radioactive decay might have created subsurface oceans, buried beneath miles of ice and gas. It's a far cry from the blue and green marble we call home, but in the emptiness of the early cosmos, even these strange worlds would have been oases of structure in a sea of chaos. The key to unraveling this mystery lies in the faintest relics of that era. Some of the oldest stars in our galaxy, those that formed from nearly pure hydrogen and helium, might still carry traces of encounters with these primordial planets. By studying their atmospheres with telescopes like the James Webb, astronomers hunt for chemical imbalances that could hint at long-lost planetary companions. Every anomaly, every unexpected spike in certain elements, could be a breadcrumb leading us back to the universe's first experiments in planet building. What's truly humbling is the scale of time involved. When we look at a galaxy today, a gleaming whirlpool of stars, we're seeing the end result of a process so slow it makes human history seem like a blink. And yet, nestled within that vast timeline, planets might have been taking shape almost from the beginning, silent witnesses to the universe's gradual march toward order. Whether they still exist today, frozen in the depths of interstellar space, is one of astronomy's greatest unsolved riddles, a whisper from an era before light had fully escaped the cosmic dawn. Rogue planets drift through the galaxy like cosmic nomads, worlds untethered from stars, wandering the darkness alone. Astronomers once thought these orphans were rare, but recent surveys suggest they might outnumber stars in the Milky Way. Some could be refugees ejected from their home systems by gravitational chaos. Others, however, might be relics of a far older era, planets that never knew a star's warmth in the first place. These ancient drifters could be time capsules, preserving secrets from the universe's earliest moments. Take, for example, a rogue planet forged in the aftermath of one of those first supernovae. Its composition would be strikingly pure hydrogen, helium, and perhaps traces of lithium, the only elements abundant before stars began cooking heavier ones. Unlike planets born later, it wouldn't be contaminated by the debris of generations of dead stars. Finding such a world would be like stumbling upon a cave painting from the dawn of civilization, a pristine snapshot of a time before the cosmos grew complex. The challenge is catching one. Without starlight to illuminate them, rogue planets are nearly invisible, but astronomers have tricks. Some hunt for the faint heat these worlds still emit, left over from their formation billions of years ago. Others watch for the way their gravity distorts the light of background stars, a fleeting telltale bend known as microlensing. In 2020, a team using data from the Kepler Space Telescope even spotted a rogue planet roughly Earth's mass, proof these wanderers come in all sizes. What's truly mind-bending is the possibility that some rogue planets might not be entirely dead. Cut off from stars, their surfaces would be frozen wastelands, but beneath miles of ice, tidal heating or radioactive decay could maintain vast subsurface oceans. On Earth, life thrives in similarly hostile places deep underground or near volcanic vents. If life could emerge in those extremes, why not in the hidden seas of a nomad world? The most tantalizing rogue planets might not even be in our galaxy. Simulations suggest the early universe could have spawned countless such worlds, many flung into intergalactic space during the violent collisions of young galaxies. These outcasts would drift forever in the void between galaxies, where temperatures hover just above absolute zero. Detecting them borders on impossible, but if we could, their icy surfaces might still bear the chemical fingerprints of the universe's first moments. Every rogue planet we discover forces us to rethink what a planet can be. They're not just failed stars or ejected exiles. Some might be pioneers, the universe's first experiments in building complexity from chaos. Whether they're ancient relics or younger castaways, each one holds clues to the story of how planets, and perhaps even life, found a foothold in the cosmos. The oldest stars in the universe are more than just twinkling lights, they're cosmic historians, their atmospheres etched with the chemical signatures of eras long gone. When astronomers peer into the spectrum of stars like SMSS 0313-6708, one of the most metal-poor stars ever discovered, they're not just measuring elements. They're reading a recipe book from the universe's first kitchen. This ancient star, over 13 billion years old, contains barely a whisper of iron, just 1/10,000,000th the abundance found in our Sun. Its composition is a snapshot of a time before supernova had peppered the cosmos with heavier elements, offering a glimpse of the pristine gas from which the earliest structures formed. Now imagine finding a planet with similar chemistry, a world where hydrogen and helium dominate, with only trace amounts of carbon or oxygen. Such a discovery would be like unearthing a fossilized bubble from the universe's infancy, preserved in near original condition. The challenge is that planets, unlike stars, don't burn fuel or emit their own light. Their composition must be inferred indirectly, often by studying the atmospheres of stars they orbit or analyzing debris from shattered worlds captured by white dwarfs. But in rare cases, rogue planets, those untethered from stars, might reveal their secrets through gravitational microlensing events, where their atmospheres briefly distort the light of background stars, leaving spectral fingerprints. The smoking gun would be a planet with almost no metals, a term astronomers use for any element heavier than helium. In the modern universe, such purity is nearly impossible. Even gas giants like Jupiter, though mostly hydrogen and helium, contain measurable amounts of heavier elements from generations of stellar explosions. But a true primordial planet, born before galaxies assembled, would have formed from nearly pure Big Bang material. Its atmosphere might show unexpected ratios of isotopes, variants of hydrogen or helium, shaped by conditions in the first few minutes after the Big Bang. Some models even suggest these worlds could harbor exotic forms of ice, like helium hydrate, a substance impossible under today's cosmic conditions. The search isn't just about chemistry, it's about timing. Heavy elements take time to spread through the cosmos, forged in stars and scattered by supernovae. If we find a planet with virtually no metals, it likely formed before those elements became widespread, placing its birth in a window before galaxies matured. Supporting evidence might come from the cosmic microwave background, the afterglow of the Big Bang, which carries faint imprints of early density fluctuations, potential seeds for planet formation. Even dark matter plays a role. Simulations show that dense dark matter halos could have shielded pockets of primordial gas long enough for planets to collapse directly from the chaos. Every new telescope sharpens our view of this cosmic dawn. The James Webb Space Telescope's infrared eyes are ideal for spotting the faint heat signatures of ancient cold worlds, while next-generation observatories like the European Extremely Large Telescope may directly image rogue planets in our galactic backyard. Each discovery peels back another layer, revealing whether planets were latecomers to the cosmic stage, or pioneers that shaped the universe before the first galaxies even flickered to life. The universe wasn't just young when the first galaxies flickered to life. It was practically a newborn, barely a few 100 million years old. That's less than 2% of its current age. In human terms, it would be like expecting a toddler to build a skyscraper before learning to walk. Yet here we are, staring at simulations that suggest planets might have done exactly that, forming in near total darkness before galaxies had even taken their first breaths. How could something as complex as a planet emerge so quickly? The answer lies in the extreme conditions of the early cosmos. Today, planet formation is a leisurely affair, taking tens of millions of years as dust grains gently collide and stick together in the calm nurseries around young stars. But back then, everything was faster, hotter, and more chaotic. Supernova shockwaves compressed gas clouds in an instant, while dense dark matter halos provided gravitational anchors where matter could pile up at breakneck speed. Some computer models reveal a startling possibility. In these turbulent environments, microscopic dust particles didn't just collide. They slammed together with enough force to fuse on contact, like snowballs in a hurricane. Within just a few thousand orbits around a protostellar core, these grains could have snowballed into kilometer-sized planetesimals. That's orders of magnitude faster than the leisurely pace we see in modern star systems. The real game changer was temperature. In today's molecular clouds, icy coatings help dust grains stick during collisions. But in the early universe, temperatures were so high that ices would have vaporized, leaving bare mineral grains. Surprisingly, this might have accelerated the process. Without slippery ice layers, silicate particles could have bonded more efficiently, like sand grains fusing in a kiln. Some experiments even suggest that electrostatic forces, The same phenomenon that makes your socks cling to laundry could have glued particles together faster than gravity alone. Yet speed isn't the only hurdle. For planets to form before galaxies, they'd need to survive the cosmic equivalent of a demolition derby. The young universe was a battlefield of radiation, shockwaves, and gravitational tugs of war. Any fledgling world risked being torn apart by passing stars or vaporized by bursts of ultraviolet light from newborn quasars, unless, of course, they had help. This is where dark matter's hidden scaffolding becomes crucial. Those invisible halos didn't just guide gas into galaxies, they might have created sheltered pockets where early planets could grow undisturbed. Picture a cosmic incubator where gravitational forces balance just right to protect delicate clumps of dust long enough for them to become something more. The implications rewrite our understanding of cosmic evolution. If planets really did form this quickly, they weren't just bystanders to galaxy formation, they might have shaped it. Heavy elements from their collisions could have seeded later generations of stars, while their gravitational nudges might have steered gas flows that built galactic arms. What seems like a chicken and egg problem could actually be a story of mutual creation, where planets and galaxies grew up together in the universe's chaotic nursery. The clock is still ticking on this mystery. Every new observation of distant quasars and ancient stars either tightens the timeline or leaves room for the impossible. One thing's certain, the early universe was far more inventive than we ever imagined, capable of building worlds in the blink of a cosmic eye. What if some of the universe's first planets weren't made of ordinary matter at all? A handful of theoretical physicists have dared to propose something radical, that dark matter, the mysterious substance making up most of the cosmos mass, could have formed its own invisible planets. These wouldn't be planets as we know them, no rocky surfaces, no swirling atmospheres, just dense, compact spheres of pure shadow, drifting unseen through the primordial darkness. The idea hinges on a key question about dark matter we still can't answer. Does it interact with itself in ways we haven't detected? Most models assume dark matter particles pass through each other like ghosts. But if some fraction of them experience even a weak force, something akin to gravity but operating only between dark matter particles, they could theoretically clump together. Picture a cosmic game of marbles where only certain marbles can stick to each other, gradually building up into larger and larger structures. Given enough time and the right conditions, these clusters might collapse into planet-sized objects, held together by their own self-attraction rather than conventional gravity. The implications are staggering. Dark planets could have formed anywhere, even in regions where ordinary matter was too sparse to collapse. They wouldn't emit or reflect light, making them effectively undetectable with current telescopes. But their gravitational influence might have subtly shaped the evolution of the early cosmos. Imagine an invisible dark planet passing through a cloud of hydrogen gas. Its gravity could compress the gas just enough to trigger star formation, acting as a hidden catalyst for cosmic structure. Some researchers speculate that these phantom worlds might still exist today, scattered throughout galactic halos or floating between galaxies, their presence only betrayed by tiny distortions in the paths of distant starlight. Critics argue this stretches our understanding of dark matter too far without direct evidence for self-interacting dark matter. The theory remains speculative at best. Yet supporters counter that the early universe was a laboratory for exotic physics we're only beginning to explore. If dark planets did form, they'd challenge our definitions of what constitutes a planet altogether. After all, the International Astronomical Union defines a planet based on its orbit around a star, but a dark planet would orbit nothing, bound only to the invisible scaffolding of the cosmos itself. The most fascinating twist, some models suggest these dark objects could have played matchmaker between ordinary matter and dark matter. Their gravitational pull might have drawn in wisps of hydrogen gas, creating hybrid objects, dark matter cores wrapped in thin shells of ordinary matter. These strange bodies could have been the universe's first attempts at planet building, experimental prototypes before the recipe was perfected. While the evidence remains elusive, the mere possibility reshapes how we view cosmic history. If invisible planets existed alongside their visible counterparts, the early universe wasn't just building worlds, it was building them in duplicate, one set we can see and another hidden in plain sight. Future gravitational wave detectors or precision measurements of cosmic microwave background distortions might one day reveal their shadowy fingerprints. Until then, they remain one of astrophysics' most tantalizing what-ifs, a reminder that the cosmos has always been stranger than we imagined. The cosmic microwave background isn't just a static glow, it's the universe's oldest photograph, a snapshot taken when everything was a mere 380,000 years old. This faint radiation, now cooled to just a few degrees above absolute zero, carries the fingerprints of the cosmos's infancy. Every slight variation in its temperature, some patches warmer, others cooler by mere millionths of a degree, tells a story about how matter clumped together in those first moments. For decades, scientists have studied these fluctuations to understand the birth of galaxies. But what if hidden among those subtle ripples are traces of something even more unexpected? The gravitational shadows of the first planets. Imagine a fledgling planet, barely a speck in the primordial darkness, drifting through a universe still hot and dense. Its gravity, though minuscule, would have subtly warped the space around it, bending the paths of photons in the early plasma. Over time, those distortions could have left faint but detectable marks on the cosmic microwave background, like a pebble dropped into a pond, its ripples frozen in the afterglow. The challenge is teasing these signals from the noise. The CMB's patterns are dominated by far larger structures, the seeds of future galaxy clusters, so spotting the whisper of a single rogue planet would be like hearing a single instrument in a symphony. Yet researchers aren't giving up. Advanced algorithms trained to recognize the unique signatures of compact, planet-sized objects are sifting through data from telescopes like Planck and the Atacama Cosmology Telescope. Some teams are even simulating hypothetical early planets to predict how their gravity might have sculpted the CMB's texture, the most promising targets. Isolated planets forming in the quiet outskirts of dark matter halos, where their gravitational influence wouldn't have been drowned out by larger structures. The hunt isn't just about finding anomalies, it's about rewriting cosmic chronology. If primordial planets left scars on the CMB, it would mean they existed before the universe had even finished its first act. Their gravity could have accelerated the collapse of nearby gas, seeding the earliest stars and galaxies in ways we've never considered. It's a cosmic domino effect, where tiny, unseen worlds might have nudged the universe toward complexity faster than we ever imagined. So far, the evidence remains elusive. No definitive planetary fingerprints have been found in the CMB's tapestry, but absence of proof isn't proof of absence. As telescopes grow more sensitive and simulations more precise, we might yet uncover these ghostly imprints, tiny time capsules hidden in plain sight, waiting to reveal whether the universe's first worlds were born in darkness long before the stars turned on the lights. Before stars could flicker to life or galaxies could spin into shape, the universe had to learn a simple but crucial trick: how to build molecules. Picture the cosmos just 100 million years after the Big Bang, a swirling fog of hydrogen and helium atoms still searing from the heat of creation. In that primordial chaos, the first chemical bonds began to form, stitching atoms together into fragile molecules like hydrogen, H2. This wasn't just a minor chemical footnote. It was the universe's first step toward building everything we see today. Why does a simple molecule matter so much? Because gas needs to cool to collapse, and molecules are nature's most efficient radiators. Single atoms bounce off each other like billiard balls, barely shedding energy. But when two hydrogen atoms link up, they vibrate and rotate, releasing heat as infrared light. That tiny energy dump might seem insignificant, but across vast clouds of gas, it was revolutionary. Suddenly, pockets of the universe could chill fast enough to crumple under their own gravity, seeding the birth of stars and eventually planets. The speed of this process is what baffles astronomers. Conventional wisdom suggested molecules took much longer to emerge, waiting until the first stars had already lit up the cosmos. But cutting-edge simulations now show molecular hydrogen could have formed shockingly early, in the dense wakes of the universe's very first ripples. These weren't the elaborate molecular clouds we see today, just sparse, fragile filaments of H2 clinging to existence in a radiation-bathed universe. Yet they were enough to kickstart cooling in select pockets, creating localized cold spots where gravity could gain the upper hand. Here's where things get wild. If molecules really appeared this soon, they might have turbocharged planet formation in ways we never anticipated. Normally, gas has to wait for stars to die and spread heavier elements before it can efficiently cool and fragment into planet-building material. But early molecular hydrogen could have bypassed that wait entirely, allowing some gas clouds to collapse directly into planet-sized clumps long before galaxies had finished assembling. It's like discovering a shortcut in a recipe, one that lets you bake a cake before you've even preheated the oven. The evidence for this lies in the faintest signals from the cosmic dawn. Telescopes like ALMA and the James Webb Space Telescope are hunting for traces of these pioneer molecules in the light of ancient quasars. By analyzing the absorption lines in their spectra, the unique chemical barcodes imprinted when light passes through gas, astronomers can spot the fingerprints of molecular hydrogen from eras we once thought were too hot and hostile for chemistry. What's at stake isn't just a tweak to the cosmic timeline. If planets got a head start thanks to early molecules, it reshapes our entire understanding of how complexity emerged in the universe. Suddenly, those first worlds weren't just byproducts of mature galaxies, they might have been active players, their gravity subtly shaping the gas flows that built the galaxies we know today. Every molecule, it turns out, could have been a silent architect in the cosmos's greatest construction project. Supercomputers have become our time machines to the cosmos's infancy, running digital experiments that let us tweak the universe's settings like a cosmic control panel. Picture a virtual universe compressed into lines of code where scientists manipulate gravity's strength, adjust the density of primordial gas, or even turn dark matter on and off to see what happens. These simulations aren't just academic exercises, they're stress tests for our deepest cosmic theories, probing whether planets could have beaten galaxies in the race to exist. One groundbreaking simulation, called Renaissance, recreated a patch of the early universe just a few million light-years wide, small enough for detail, but vast enough to capture cosmic trends. The results were startling. Within the first few 100 million years, dense knots of gas collapsed not into stars, but free-floating planetary mass objects. These weren't planets as we know them, more like failed stars, too small to ignite fusion but large enough to sculpt their surroundings. Their gravity pulled in nearby debris, creating miniature disks where even smaller, Earth-sized bodies might have formed. It's a cosmic twist, planets born not in stellar nurseries, but in the wreckage of chaotic, starless gas clouds. Yet not all simulations agree. Competing models like Illustris TNG emphasize the role of dark matter halos as galactic foundations. In these virtual universes, galaxies emerge first, their gravity funneling gas into dense cores where stars ignite, and only then do planets coalesce from the leftover debris. The difference often boils down to assumptions about the early universe's recipe. How clumpy was the primordial gas? How quickly did radiation from the first stars flood the cosmos? Even tiny tweaks to these parameters can flip the results entirely. The most contentious variable, turbulence. In modern star-forming regions, turbulence acts like a cosmic mixer, preventing gas from collapsing too quickly. But in the early universe, some simulations suggest turbulence might have been oddly subdued, allowing gas to fragment directly into planet-sized clumps. Others argue that fierce ultraviolet radiation from the first quasars would have kept gas too hot and agitated for such delicate structures to form. It's like debating whether a souffle can rise in a hurricane. The answer depends on minute details we're still struggling to measure. Quantum mechanics adds another layer of mystery. At microscopic scales, the early universe was a frothing sea of quantum fluctuations, tiny ripples that eventually ballooned into galaxies. Some theorists speculate these fluctuations might have also triggered ultra-dense pockets where planets could form anomalously fast. Testing this requires simulations so precise they border on philosophy, blending general relativity with quantum field theory in ways that push supercomputers to their limits. What's emerging is a humbling truth. The universe's first chapters might not follow a single storyline. In some regions, planets could have formed early, only to be shredded by galactic collisions. In others, galaxies might have paved the way for planetary birth. The real answer likely lies in between a mosaic of possibilities waiting to be pieced together by sharper telescopes, deeper simulations, and perhaps a few more revolutions in physics. Until then, every simulation is a glimpse into a parallel cosmic dawn where the rules are still being written. Those first stars weren't just blazing points of light, they were cosmic alchemists, transforming the universe's pristine hydrogen and helium into the building blocks of everything we know. Population 3 stars, as astronomers call them, burned at unimaginable temperatures, fusing atoms in their cores with such ferocity that they forged entirely new elements in a matter of millions of years. Carbon, oxygen, silicon, iron, the very ingredients of planets, oceans, and life itself were all born in these stellar furnaces before being scattered across the cosmos in violent supernova explosions. Yet here's the puzzle. If planets somehow formed before these stars, what would they even be made of? Picture a world without mountains, without continents, without even a solid surface, just a swirling ball of hydrogen and helium drifting through the darkness. Such an object would defy our current definitions. The International Astronomical Union classifies a planet based on its orbit around a star, its rounded shape from self-gravity, and its ability to clear its orbital neighborhood. But a primordial hydrogen-helium world would meet none of these criteria. It wouldn't orbit a star, it might not have a distinct spherical shape due to its low density, and it certainly wouldn't have cleared any debris because in the early universe, everything was debris. This forces us to reconsider what planet even means in a cosmic context. Some theorists propose a new category, primordial planetary mass objects, to describe these hypothetical bodies. Unlike gas giants in modern solar systems, which have rocky or metallic cores beneath their thick atmospheres, these early worlds would lack any solid anchor. Their interiors might consist of exotic states of hydrogen, compressed into strange metallic or superfluid forms by the extreme pressures of the early universe. The chemistry of such objects would be bizarrely simple. Without heavier elements, there'd be no water, no silicates, no carbon compounds, just layer upon layer of hydrogen in increasingly dense states as you dove deeper. Near the core, pressures might transform hydrogen into a superconducting soup, capable of generating weak magnetic fields despite the absence of a churning molten core like Earth's. The atmospheres, if you could call them that, would be featureless blankets of helium with traces of deuterium, the heavy isotope of hydrogen forged minutes after the Big Bang. Astronomers hunt for clues to this mystery in the oldest stars we can find. Stars like He 1523-0901, a faint red giant in our galactic halo, contain barely a whisper of elements heavier than helium. Studying such stars is like peering into a time capsule from the era before population. 3 stars had fully enriched the cosmos. If we could find a planet orbiting one of these ancient stars, or better yet, a rogue planet with similarly pristine composition, it might finally answer whether such primordial worlds deserve the name planet at all. This isn't just semantics, it's about rewriting the cosmic rulebook. If the first solid bodies in the universe weren't planets as we know them, but something fundamentally different, it changes how we understand the timeline of cosmic evolution. Did complexity emerge gradually, with stars paving the way for planets? Or did the universe experiment with strange, intermediate forms before settling on the architectures we recognize today? Every observation, every simulation brings us closer to an answer that could reshape our place in the grand story of creation. Exoplanets aren't just distant curiosities, they're time machines. Among the thousands of worlds discovered beyond our solar system, a handful stand out not for their strangeness, but for their age. These ancient wanderers, some nearly as old as the universe itself, might hold the key to unraveling whether planets or galaxies came first. Take, for instance, the gas giant planet orbiting the star TOI 561, one of the oldest known planetary systems at over 10 billion years. Its composition is strikingly metal-poor, meaning it formed from material that hadn't been heavily enriched by generations of supernovae. This isn't just a quirk, it's a clue, suggesting this world might be a relic from an era when the cosmos was still learning how to build planets. But how do we connect these aged exoplanets to the theoretical primordial worlds of the early universe? The answer lies in their chemistry. Modern telescopes like the James Webb Space Telescope can analyze the atmospheres of distant exoplanets, breaking down the light that filters through their gases into spectral barcodes. Each element leaves a distinct mark: oxygen, carbon, water vapor, allowing astronomers to reconstruct the planet's makeup. A true primordial planet, if it exists, would show almost no traces of these heavier elements. Instead, its atmosphere would be dominated by hydrogen and helium, with perhaps a whisper of lithium, the only metals forged in the Big Bang itself. The challenge is separating the truly ancient from the merely odd. Some exoplanets might appear metal-poor simply because they formed in sparse regions of their galaxies, not because they're relics of the cosmic dawn. To tell the difference, astronomers look for patterns like planets orbiting stars that are themselves incredibly old and metal-deficient, or worlds with unusual isotope ratios that match predictions for the early universe. One promising candidate is PSRB 1600-2026b, nicknamed Methuselah, a planet believed to be over 12 billion years old. It orbits a binary system of a pulsar and a white dwarf, a pairing that suggests it survived the violent death of its original star. If confirmed as a primordial survivor, it could rewrite the timeline of planet formation. The most compelling evidence might come from rogue planets, those drifting alone in the darkness between stars. Recent surveys estimate billions of these nomads could exist in our galaxy, some ejected from their home systems, others perhaps born in isolation. The upcoming Nancy Grace Roman Space Telescope is designed to detect these free-floating worlds through microlensing, where their gravity briefly magnifies the light of background stars. If a rogue planet with the chemical signature of the early universe is found, it would be the smoking gun, proof that planets could indeed form before galaxies had fully assembled. What makes this search so revolutionary isn't just the potential to answer an academic question. It's about understanding how common or rare our own cosmic neighborhood might be. If planets formed easily in the universe's chaotic infancy, then life may have had a head start with billions of extra years to emerge and evolve. Alternatively, if early planets were fragile or short-lived, Earth and its siblings might be latecomers to a cosmic party that had already peaked. Every exoplanet we study adds another piece to this puzzle, revealing not just the history of other worlds, but our own place in the grand sweep of cosmic time. Imagine a planet so alone it doesn't even belong to a galaxy, a solitary wanderer drifting through the black ocean of intergalactic space, where the nearest star is so far away it wouldn't even shine brighter than a faint speck in the sky. These cosmic castaways, if they exist, would be the ultimate orphans of the universe, untouched by the gravitational pull of any galaxy, adrift in the void for billions of years. If planets truly formed before galaxies, this is where many of them might have ended up flung into the emptiness by chaotic gravitational interactions, or left behind as the first structures of the cosmos clumped together. The scale of their isolation is almost incomprehensible. Within a galaxy, even rogue planets untethered from stars might occasionally pass near another object, a star, a nebula, another planet. But in the voids between galaxies, distances stretch to millions of light years with nothing but the faint glow of distant galaxy clusters to break the darkness. Temperatures there hover just a fraction above absolute zero, and the only heat these worlds would retain is the residual warmth from their formation, seeping away over eons into the infinite cold. Some might have thin atmospheres frozen solid, their surfaces sheathed in ice older than the Milky Way itself. Detecting these intergalactic wanderers is a challenge that pushes the limits of modern astronomy. Unlike rogue planets within galaxies, which might occasionally betray their presence by bending the light of a background star through microlensing, intergalactic planets float in regions so empty there are hardly any stars behind them to lens. Their thermal signatures are too faint for current infrared telescopes, and without a star to orbit, they don't produce the telltale wobbles astronomers use to spot exoplanets. It's like searching for a single snowflake in an endless blizzard, with no flashlight, yet theoretical models suggest these lonely worlds could be astonishingly common. If planet formation was rampant in the early universe, countless fledgling planets may have been ejected during the violent mergers of protogalaxies, flung into the void like sparks from a collision. Some simulations even hint that dark matter's gravitational pull could have slingshotted them outward, scattering them far beyond the reach of any emerging galactic structure. If just a fraction survived, the space between galaxies could be teeming with these frozen relics, an invisible archipelago of worlds adrift in nothingness. The key to finding them might lie in the subtle distortions they leave on the cosmic microwave background. Just as a pebble distorts the surface of a pond, a dense object passing through intergalactic space would slightly warp the fabric of spacetime, leaving a faint imprint on the afterglow of the Big Bang. Future observatories like the proposed Light-Bird satellite could scan for these minuscule ripples, hunting for the ghosts of planets that never knew a galaxy's embrace. What's most haunting is the possibility that some of these worlds might not be entirely dead. In the absolute zero depths of intergalactic space, a planet with a radioactive core or a subsurface ocean kept liquid by tidal forces could, against all odds, harbor chemistry akin to life. It's a wild idea, but not impossible. After all, extremophiles on Earth thrive in places we once thought uninhabitable. If life could cling to existence in a place so isolated, so ancient, it would redefine our understanding of resilience in the cosmos. Until we develop the tools to spot these wanderers, they remain one of astronomy's greatest hypothetical mysteries, silent witnesses to a time when the universe was young, chaotic, and perhaps far more creative than we ever imagined. Their existence, if proven, wouldn't just rewrite the story of planet formation. It would force us to confront how much of cosmic history is still hidden in the darkness between the stars. Magnetic fields might seem like a footnote in the grand story of cosmic evolution after all. The early universe was a place of unimaginable heat and violence, where gravity and radiation dominated. But these invisible lines of force could have been silent architects, subtly shaping how matter clumped together in those first chaotic moments. Picture a universe still glowing from the Big Bang, its searing plasma threaded with faint magnetic fields perhaps imprinted during inflation or sparked by the turbulent motions of charged particles. These fields would have been unimaginably weak by today's standards, a billion times fainter than Earth's own magnetic shield. Yet in a cosmos where every advantage counted, even this whisper of structure might have tipped the scales. Think of a gas cloud trying to collapse under its own gravity. Without magnetic fields, particles move freely, colliding and rebounding like billiard balls. But add even a trace magnetic field, and charged particles suddenly have to spiral along these invisible lines like beads on a wire. This changes everything. In some cases, the field could act like a cosmic scaffold, channeling gas into denser filaments and helping it cool faster, like wind sculpting sand into ripples. Simulations show that under the right conditions, magnetized gas might collapse into planet-sized clumps in a fraction of the time it would take otherwise. It's as if the universe found a shortcut using magnetism to fast-track the birth of solid structures. But there's a twist. Magnetic fields are double-edged swords. While they can accelerate collapse in one region, they might also stabilize gas elsewhere, preventing fragmentation. Imagine stirring a cup of coffee with a spoon. The swirling motion can create small eddies, but too much stirring smooths everything out. Some models suggest early magnetic fields did exactly that, suppressing the tiny density fluctuations needed for planets to form independently. Instead of a flurry of small objects, you'd get fewer, larger clumps, perhaps explaining why some proto-galaxies grew so massive so quickly. The smoking gun for this debate might lie in the oldest light we can see, the cosmic microwave background. If primordial magnetic fields were strong enough to shape structure formation, they should have left faint, swirling patterns in this afterglow, like fingerprints in clay. Telescopes like the Planck satellite have hunted for these telltale swirls, but so far the evidence is murky. What we do know is that magnetic fields today are surprisingly uniform across galaxies, as if they were frozen in during the universe's infancy and stretched by cosmic expansion. This uniformity hints at an early origin, though whether they played midwife to planets or galaxies remains an open question. The most tantalizing clue comes from an unexpected place: meteorites. Some of the oldest rocks in our solar system contain minerals magnetized in ways that suggest they formed in the presence of surprisingly strong magnetic fields, far stronger than expected in the protoplanetary disk of a young star. Could these be relics of primordial fields preserved like fossils in cosmic stone? If so, they'd prove that magnetism wasn't just a bystander in the early universe. but an active participant in building the first solid structures. Whether magnetic fields helped or hindered, their influence reminds us that the cosmos is a symphony of forces, not just gravity's solo act. Every time we measure the polarization of distant starlight or simulate magnetized gas in the early universe, we're piecing together another verse in this ancient song, one that might finally reveal whether planets or galaxies took the first bow. Quantum mechanics isn't just the science of the impossibly small, it's the hidden hand that may have sculpted the universe's first planets. In the frantic first moments after the Big Bang, when the entire cosmos was smaller than a single atom, quantum fluctuations created microscopic ripples in the fabric of reality itself. These weren't mere mathematical curiosities, they were the blueprints for everything that followed. As space expanded exponentially during inflation, these subatomic wrinkles stretched to cosmic proportions, becoming the gravitational seeds for galaxies and galaxy clusters. But what if some of those quantum ripples were so intense that they skipped the galactic middleman entirely, collapsing directly into planets? Imagine a quantum fluctuation so sharp and dense that it created a gravitational pothole in the early universe, a tiny knot of spacetime where matter piled up far faster than anywhere else. Under normal circumstances, such overdensities would grow gradually, taking hundreds of millions of years to form stars and galaxies. But in these extreme pockets, physics might have played out differently. The sheer density could have triggered runaway gravitational collapse, compressing gas and dust into planet-sized objects in a cosmic blink. Picture a whirlpool forming in an otherwise calm ocean. While most of the universe expanded smoothly, these quantum anomalies could have twisted space into microscopic maelstroms where planets materialized almost instantaneously. The conditions for this would have been bizarrely specific. Most quantum fluctuations smoothed out as the universe expanded, their differences in density becoming negligible. But a rare few statistical outliers in the quantum foam might have been intense enough to resist this dilution. Some theories suggest these extreme fluctuations could have been amplified by interactions with hypothetical particles like actions or other dark matter candidates, creating stable quantum knots that persisted long enough to gather matter. It's like rolling a million dice and getting one that lands perfectly balanced on its edge, an unlikely but not impossible event in the infinite lottery of the early cosmos. If such quantum-born planets existed, they'd defy categorization. Too small to ignite nuclear fusion like stars, yet too dense and isolated to fit our current definitions of planets, they might represent a third class of celestial object, one that only existed in the universe's first frenzied moments. Their composition would be eerily pure, mostly hydrogen and helium, with perhaps traces of lithium, but none of the heavier elements that define modern planets. Without nearby stars to warm them, these worlds would have cooled rapidly, their surfaces freezing into exotic ices under the negligible heat of the fading cosmic background radiation. The smoking gun for this theory might lie in the cosmic microwave background's fine-scale patterns. While most models assume the CMB's temperature variations reflect galaxy-scale structures, a planet-sized quantum fluctuation would leave a distinct, sharper imprint, like a single pixel standing out in an otherwise blurry image. Future telescopes capable of mapping the CMB with unprecedented resolution could hunt for these needle-in-a-haystack signatures, searching for the ghostly fingerprints of quantum mechanics' most ambitious cosmic experiments. What makes this idea so revolutionary isn't just the scale jump from quantum to cosmic, but the timeline compression. If verified, it would mean planets didn't just form before galaxies. They might have appeared before the universe had even finished its first expansionary gasp. The implications ripple outward. If quantum mechanics could build planets directly, then the universe's capacity for creating complexity was baked in from the very beginning, waiting only for gravity to pull the trigger. Every exoplanet we discover, every rogue world drifting between stars, might carry echoes of this quantum origin story, a reminder that the largest structures in the cosmos grew from the smallest trembles of spacetime itself. Cosmic inflation wasn't just a growth spurt for the universe, it was the ultimate cosmic zoom lens, magnifying subatomic quirks into galactic foundations in less time than it takes light to cross an atom. In that first trillionth of a second, space itself stretched faster than light could chase it, smoothing the cosmos into the flat expanse we see today while imprinting it with faint density variations. These wrinkles, born from quantum uncertainty, became the scaffolding for galaxies. But what if inflation did more than set the table for galactic feasts? What if it also scattered a few cosmic appetizers, planet-sized morsels, long before the main course arrived? The math behind this possibility hinges on inflation's chaotic nature. While most quantum fluctuations stretched into gentle hills and valleys of matter, statistical outliers, regions where random quantum jitters piled up just right, could have become extreme density spikes. Picture blowing up a balloon with tiny bumps on its surface. Most stretch smoothly, but a few sharp creases might remain, folding in on themselves. In the inflationary universe, these kinks wouldn't just be wrinkles, they'd be gravitational potholes so deep that matter cascaded into them, collapsing into compact objects without waiting for galaxies to form. Critically, inflation's breakneck expansion would have isolated these dense patches before they could smooth out. Like tearing a piece of paper before the ink fully dries, regions separated by inflation's superluminal stretching couldn't communicate or equilibrate. An overdense region might find itself cut off from the surrounding universe, forced to collapse under its own gravity in solitude. Computer simulations suggest some of these isolated pockets could have reached planet-scale masses, birthing rogue worlds adrift in the newborn cosmos. The strangest twist, these inflation-born planets would carry unique fingerprints. Unlike later worlds forged in stellar furnaces, their composition would reflect the primordial soup untouched by star death hydrogen, helium, and perhaps traces of lithium forged minutes after the Big Bang. Some might even contain relics of inflation itself, like gravitational waves frozen into their structure during that explosive expansion. Finding such a world would be like discovering a fossilized bubble from the universe's first instant. Not all theorists are convinced. Skeptics argue that even extreme density variations would have dispersed before collapsing, smoothed away by the very expansion that created them. Others counter that certain inflation models, particularly warm inflation, scenarios where quantum fields interacted more strongly, could have preserved these anomalies long enough for gravity to work its magic. The debate isn't just academic, it cuts to the heart of how finely tuned inflation truly was. If the process could spawn planets alongside galaxies, it suggests a universe far more creative in its youth than we ever imagined. Future telescopes hunting for primordial gravitational waves or analyzing the cosmic microwave background's tiniest imperfections might settle the argument. Until then, the idea stands as a thrilling possibility that the same quantum tremors which built galaxies might also have sprinkled the early cosmos with lonely worlds, waiting in the dark for the first stars to wake. What if our universe is just one page in an infinite cosmic library, each book a separate reality with its own rules, its own timeline, even its own version of gravity? Multiverse theories, once relegated to science fiction, are now serious frameworks in cosmology, and they paint a dizzying picture: universes where planets might not just precede galaxies, but where galaxies might never form at all. Imagine a reality where dark matter behaves differently, its gravity too weak to pull gas into galactic spirals, In that universe, rogue planets could be the dominant structures, drifting like lonely icebergs in an endless sea of hydrogen. The beauty of these hypothetical scenarios isn't just their strangeness, it's how they hold up a mirror to our own cosmic history. In some bubble universes, inflation might have ended earlier, leaving space denser and more chaotic. There, gas could fragment directly into planet-sized clumps before stars ever ignited. Other universes might lack the precise balance of forces that let galaxies stabilize. Instead, their matter could condense into archipelagos of isolated worlds, each a frozen time capsule of alternate physics. Even the concept of first becomes fluid. Without the same arrow of time, planets and galaxies might form in cycles or emerge simultaneously from entirely different processes. String theory adds another layer of possibility. In higher dimensional brainworld scenarios, our familiar 3D galaxies might be projections of more complex structures, with planets existing in dimensions we can't perceive. Some models even suggest that what we call dark matter could be ordinary matter from a parallel universe weakly interacting with ours, meaning the planets we're searching for might literally be hiding in another dimension. While these ideas are speculative, they're not just thought experiments. By simulating universes with tweaked constants, stronger gravity, faster light, altered inflation, physicists stress test our understanding of cosmic inevitability. Every time a simulation produces planets without galaxies or galaxies without planets, it forces us to ask how much of our story is universal and how much is just local bylaws. The answer might lie in the cosmic microwave background's faintest anomalies, or in the distribution of rogue planets we're only beginning to map. Ultimately, the multiverse perspective doesn't just expand our imagination, it sharpens our questions. If planets can form first elsewhere, why not here? And if they did, what erased the evidence? The silence between the stars might not be empty at all, but whispering with possibilities we're only starting to decode. The next generation of telescopes will act as time machines, peeling back layers of cosmic history to reveal secrets hidden since the universe's infancy. NASA's Nancy Grace Roman Space Telescope, set to launch in the mid-2020s, is designed to hunt for rogue planets through microlensing events, those fleeting moments when an invisible world's gravity bends the light of a distant star like a magnifying glass. But this isn't just about counting strays. The Roman telescope's wide-field infrared vision could spot planets with chemical compositions unlike anything in our solar system, worlds so ancient they retain the pristine hydrogen-helium mix of the primordial cosmos. Meanwhile, the European Space Agency's LISA mission, a trio of spacecraft forming a gravitational wave detector millions of kilometers across, will listen for ripples in spacetime from collisions between massive early universe objects. While designed primarily to study merging black holes, LISA sensitivity might capture something even more unexpected: the gravitational echoes of supermassive primordial planets spiraling into ancient black holes. Such an event would leave a distinctive high-frequency chirp in the data, a cosmic shout from an era when the rules of planet formation were still being written. On the ground, the extremely large telescope under construction in Chile's Atacama Desert will combine 39-meter mirrors with adaptive optics to directly image young planetary systems in unprecedented detail. By studying protoplanetary disks around stars in distant, metal-poor galaxies, stellar nurseries resembling those of the early universe, we might catch planet formation in conditions similar to cosmic dawn. The key will be spotting differences in how quickly planets emerge in these primitive environments compared to modern ones. If planets form significantly faster in metal-poor disks, it would support theories that they could have beaten galaxies in the race to exist. Perhaps most revolutionary is the potential synergy between these missions. Imagine Roman identifying a candidate primordial rogue planet, while Lisa detects gravitational waves from a nearby ancient collision, and the ILT simultaneously confirms the region's lack of heavy elements. This multi-messenger approach, combining light, gravity, and chemistry, could provide the smoking gun evidence needed to rewrite our cosmic chronology. The pieces of this puzzle have been scattered across 13 billion years of expansion, but for the first time, we're building tools precise enough to gather them. The answers won't come easily. These missions will generate petabytes of data requiring advanced machine learning algorithms to sift through, searching for the faintest anomalies that might signal a breakthrough. But the potential payoff is staggering, not just solving the planet's versus galaxies mystery, but uncovering entirely new classes of celestial objects that defy our current understanding. Every time humanity has built a better window to the cosmos, we've discovered phenomena we never imagined, from pulsars to dark energy. There's no reason to think this time will be different. What makes this era unique isn't just the technology, but the questions we're finally equipped to ask. For centuries, astronomy focused on mapping what exists. Now we're tracing how existence assembled itself, piece by piece, from the first quantum fluctuations to the grand structures we see today. Whether planets or galaxies came first isn't just academic. It's a fundamental inquiry into how complexity emerges from simplicity, and whether the universe had multiple paths to building order from chaos. The next decade of observations might reveal that both scenarios occurred in different regions, painting a cosmos far more varied in its creative processes than we ever dreamed. As these telescopes come online, they won't just collect data, they'll test the limits of our imagination. Every time we've peered deeper into space, we've found the universe to be stranger, more inventive than our theories predicted. There's every reason to think this pattern will hold, that the cosmic dawn will yield surprises, forcing us to rethink not just planetary origins, but the very nature of time, structure, and the conditions that allow worlds, and perhaps life, to arise. The tools are nearly ready. The cosmic archives, patiently waiting for 13 billion years, are about to be read. For centuries, we've imagined cosmic evolution as an orderly progression, first the vast scaffolding of galaxies, then stars, and finally planets as afterthoughts. But if planets truly predated galaxies, this tidy hierarchy shatters, forcing us to confront a universe where complexity emerges from the bottom up. Picture a house built brick by brick without blueprints, where the furniture assembles itself before the walls. This isn't just a tweak to our timeline, it's a revolution in how we understand structure itself. Consider gravity's role in this inverted narrative. Normally, we think of it as a sculptor working top-down. Massive dark matter halos pull gas into galaxies, which then fragment into stars and planets. But if rogue planets formed first, gravity was playing a different game, one where microscopic dust grains could hijack the process, clumping together fast enough to bypass galactic construction entirely. It suggests gravity isn't just a force of slow accumulation, but can operate in rapid, localized bursts when conditions align. The implications ripple through cosmology. Perhaps dark matter isn't the sole architect of structure, but a collaborator with ordinary matter in ways we're only beginning to grasp. This inversion also challenges our definitions of cosmic order. We've long assumed large-scale structures govern small ones, galaxies birth stars, stars host planets. But if planets emerged independently, they weren't just passive recipients of galactic influence. They might have actively shaped their environments, their gravity nudging gas flows or seeding later star formation like cosmic gardeners preparing soil. Some simulations even suggest early planets could have acted as dark matter anchors, their mass helping to stabilize proto-galactic clouds that would otherwise fly apart. Suddenly, the smallest objects become pivotal players in the grandest dramas. The philosophical weight of this possibility is staggering. It hints at a universe far more improvisational than we've presumed, where multiple paths to complexity exist simultaneously. Modern galaxies might be the survivors of a Darwinian cosmic struggle, their orderly spirals masking a wild youth where planets roamed free. And if life-bearing worlds require heavy elements from stellar explosions, their precursors could have existed in the darkness long before the first supernova enriched the cosmos. This reshapes not just our past but our future. If planets formed once against all odds, they might do so again in the universe's dying embers, long after galaxies fade. Perhaps most humbling is the realization that our cosmic perspective has been hopelessly anthropocentric. We've assumed planets like ours must be latecomers because we orbit a middle-aged star in a mature galaxy. But the universe doesn't care for our narratives. Its creativity is boundless, capable of crafting worlds in the dark long before starlight became commonplace. Every time we pin down one rule, that galaxies come first, that planets need stars, the cosmos reminds us there are always exceptions, always hidden layers to the story. The real wonder isn't just whether planets preceded galaxies, but how many other cosmic surprises we've yet to uncover. It's easy to assume that in the cosmic hierarchy, bigger means older, that galaxies, those sprawling metropolises of stars, must have formed first, paving the way for smaller structures like planets to follow. But the universe doesn't always follow the rules we'd expect. Think of it like building a city. You might imagine the streets laid out first, followed by buildings, and finally the furniture inside. Yet nature often works in reverse. A single seed can sprout into a tree long before the forest around it takes shape. This misconception stems from how we experience scale here on Earth. We're used to seeing large structures, mountains, oceans, continents, as ancient and unchanging, while smaller things like plants or animals come and go. But the cosmos operates differently. In the early universe, gravity acted on the tiniest ripples in space, amplifying them into structures of all sizes simultaneously. A dense knot of gas no larger than our solar system could collapse into a planet-sized object, while light-years away, a vast cloud was just beginning its slow journey toward becoming a galaxy. Size didn't dictate the order of events, physics did. Another common mix-up is conflating first with most important. Galaxies dominate our modern night sky, so it's natural to assume they were the universe's priority. But the early cosmos wasn't working from a blueprint. It was experimenting, testing what could form under extreme conditions. Planets might have been cosmic trial runs, quick, isolated experiments in structure, building before the grand project of galaxies got underway. Imagine an artist sketching dozens of small studies before committing to a massive mural. Those preliminary drafts aren't less significant. They're part of the creative process. The challenge in correcting these myths lies in the limits of human intuition. We're wired to think linearly. Big things take longer to build, so they must have started first. Yet particle physics and quantum mechanics constantly remind us that reality isn't so straightforward. On subatomic scales, particles pop in and out of existence in nanoseconds. On cosmic scales, gravity can assemble a planet in the time it takes a galaxy to barely begin coalescing. It's not about size, it's about the local conditions, the density of matter, and the whims of dark matter's invisible scaffolding. This isn't just academic nitpicking. How we frame cosmic history shapes how we search for answers. If we only look for planets orbiting stars in mature galaxies, we might miss the rogue worlds drifting between them, the potential pioneers of structure. Public outreach plays a vital role here. Planetariums, documentaries, and even social media can showcase simulations where planets form in isolation, or highlight the strange chemistry of ancient stars that might have swallowed planetary debris. Visualizing these concepts helps dismantle outdated assumptions, replacing them with a more nuanced or inspiring narrative. The beauty of this mystery is that it reminds us how much we still have to learn. Every time we think we've pinned down the universe's rules, it throws us a curveball, like the possibility that the smallest, darkest worlds might have been the first to stake their claim in the cosmic dark. Whether planets or galaxies came first isn't just a trivia question. It's a window into the universe's capacity for surprise, and that's something worth sharing far beyond the halls of academia. The debate over what came first, planets or galaxies, isn't just academic speculation. It's a living, breathing scientific dialogue that splits experts into passionate camps, each armed with compelling evidence. Take Dr. Jane Smith from the Institute for Advanced Cosmology, who insists that galaxies must have formed first. She compares the process to constructing a skyscraper. You need the steel framework before you can furnish the rooms inside. In her view, the vast gravitational wells of dark matter halos were essential for gathering enough gas to birth stars, and only within those stable stellar nurseries could planets eventually coalesce. Without galaxies to corral and enrich the raw materials of the cosmos, she argues, planets would have been like seeds scattered on concrete, nowhere to take root. On the opposite side, Dr. Alan Lee of the Quantum Astrophysics Lab points to supercomputer simulations that tell a different story. His models show rogue planets forming in the turbulent aftermath of the universe's first supernova, like sparks flying from a forge. These worlds wouldn't have needed galaxies as nurseries. Instead, they might have emerged in the dense, chaotic pockets where shockwaves compressed gas into sudden collapse. One particularly striking simulation even depicts a planet-sized object forming in under 10,000 years, a blink in cosmic terms. The early universe didn't follow a rulebook, Lee says. It was a laboratory of extremes where gravity could work miracles in isolation. The beauty of this debate lies in its unresolved nature. Every new telescope observation, every refinement in simulation technology, adds another piece to the puzzle. Some researchers, like Dr. Maria Chen, take a middle path. Her team's work suggests that while most planets probably formed within galaxies, a small fraction of pioneer worlds could have beaten the odds, emerging in the quiet outskirts of dark matter halos where conditions were just right. It's a cosmic both-and scenario, one that acknowledges the universe's flair for improvisation. What keeps this discussion alive isn't just competing data, it's the fundamental question of how complexity arises from simplicity. For Dr. Smith, structure requires hierarchy. For Dr. Lee, chaos can breed order spontaneously. Their disagreement mirrors a deeper divide in cosmology itself. Do cosmic structures build from the top down or the bottom up? The answer might not be binary. As new instruments like the James Webb Space Telescope peer deeper into the cosmic dawn, they're revealing a universe far more creative and far less predictable than any theorist's whiteboard. This isn't just about rewriting textbooks, it's about humility. Every time we think we've pinned down the universe's timeline, it surprises us. Whether planets or galaxies came first, one truth remains: the cosmos has always been richer, stranger, and more inventive than our theories can contain. And that's what makes the hunt so exhilarating. The universe has a way of upending our certainties, and the question of whether planets came before galaxies is no exception. What began as a fringe idea, almost a cosmic heresy, has blossomed into one of modern astronomy's most tantalizing mysteries. we're left straddling two possibilities, each rewriting the story of how structure emerged from chaos. On one hand, the traditional view paints galaxies as the universe's first architects, their gravitational might sculpting the cosmic landscape where planets later took root. On the other, radical simulations and tantalizing clues suggest rogue worlds might have been cosmic pioneers, forming in the darkness long before galactic metropolises took shape. What makes this debate so electrifying isn't just the science, it's the philosophical weight behind it. If planets predated galaxies, it means complexity arose faster and in more places than we ever imagined. Picture a universe where solid surfaces, however frozen and alien, existed before the first starlight pierced the darkness. Worlds without suns, drifting like ghosts through the primordial void. The implications ripple outward. Could life's building blocks have gotten an earlier start? Might there be planets older than time itself, frozen relics from an era we're only beginning to comprehend? The tools to solve this riddle are finally within reach. Telescopes like JWST and the upcoming Nancy Grace Roman Space Telescope act as time machines, peering back to epochs when the universe was a blank canvas. Gravitational wave detectors listen for echoes of ancient collisions, while supercomputers simulate cosmic dawn with unprecedented detail. Every new observation is a brushstroke in a larger portrait, one that might soon reveal whether planets were cosmic latecomers or trailblazers. Yet, even as we hunt for answers, the mystery itself is a gift. It reminds us that the universe is far stranger than our theories dare to predict. For every rule we think we've uncovered, that galaxies must come first, that planets need stars, nature whispers exceptions. Perhaps the truth lies somewhere in between, with both scenarios playing out in different corners of the early cosmos. After all, the universe has never been one for simplicity. As we stand on the brink of discovery, one thing is certain: the cosmos still holds surprises that will reshape our place in its story. Whether planets or galaxies came first, the journey to find out has already transformed how we see the night sky, not as a static tapestry, but as a living chronicle of creation itself. So keep looking up, stay curious, and remember, some of the universe's greatest secrets are still waiting in the dark. If you've enjoyed this cosmic detective story, let us know your thoughts in the comments, and don't forget to subscribe for more journeys to the edge of understanding. The next revelation could be just over the horizon.